As time moves forward, the wave function of a quantum particle doesn't stay still. It evolves. And since the wave function determines the probability of finding a particle in a given region, those probabilities also change over time. This evolution is smooth and continuous, revealing that probability doesn't stay fixed. It flows across space. Much like how we describe the flow of electric charge with current, we describe this movement of probability using probability current density. In this video, we'll walk through the steps to derive the expression for the probability current density. Let's first work with the concept of probability density. Represented by letter J, it is the likelihood of finding a quantum particle at a certain point in space. Mathematically, the probability density is given by the product of the wave function psi and its complex conjugate psi star. Now, let's take the time derivative of the probability density. This results in equation 1. To continue the derivation, we now need to understand how the wave function evolves with time. And for that, we rely on the following time-dependent Schrödinger equation. Here, m is the mass of a particle, and it experiences a potential energy V. Next, we take the complex conjugate of this equation and substitute both these equations into equation 1 and obtain the following equation. As you can see, both terms inside the brackets contain the potential energy. Since they appear with opposite signs, these potential terms cancel out, and we're left with the following much simpler equation 2. Now that we've simplified things down to equation 2, let's bring in the continuity equation. It relates the time rate of change of the probability density to the probability current density. So we'll substitute equation 2 into the continuity equation, which gives us the next step, equation 3. Now, by integrating both sides of equation 3, we arrive at the final expression for the probability current density.